So, my dear student friends, welcome back to my next lecture, that is module number 15, and what we do now, we will talk on a concept of interface mass transfer. Till now, we have discussed theoretical principles and the definitions of mass transfer from one point to the another point in a single or in a homogeneous medium by using either equations of molecular diffusion or mass transfer coefficients, right? Even when you talk about your molecular diffusion through the fluids, or when you talk about diffusion through the solids, or when you talk about mass transfer coefficients, there we discussed only when the flow is taking place within a phase, or the solute is moving from one point to the other point in the single phase. But generally, when you talk about the applications of mass transfer, we will not have a single phase. We have two phases where the two phases are contacted. When the two phases are contacted, the solute is now transferring from a phase 1 to the phase 2 through a interface, right? Any application we talk about mass transfer applications, we are not going to come across any single phases, we are going to come across the multiple phases. So when you talk about these multiple phases, we have maybe several examples we are going to discuss. Maybe absorption of air, absorption of ammonia from air into water, maybe sulfur dioxide from air into water, or separation of extraction of aromatics from kerosene using sulfolane. This is a 5-membered heterogeneous ring, that is the CH2 SO4. 5-membered heterogeneous ring contains 4 carbon molecules and 1 sulfur molecule, and so this is another problem, extraction of aromatics from the kerosene, or the drying of air using H2SO4. This is the example already we have discussed in the first module. Maybe we have a air, it is a moistened air, then we have to remove that moisture. Maybe that can be done by contacting with the H2SO4. Then aeration of the pool of water in an aquarium. So these are the examples where we are not going to discuss about say mass transfer in a single phase. We are going to come across the mass transfer in the two phases. So in all of the examples, the mass transfer substance is transferring from the one phase to the other phase. That is the reason we call it as a interphase mass transfer. And what we need to have, we have to calculate the rate of mass transfer in phase 1. We have to calculate the rate of mass transfer in phase 2, and at steady state, how much of mass that is transferred from the phase 1 to the phase 2, the same amount of mass that is transferred from the phase maybe interface to the phase 2. So what we can do, we can do separate calculations for the phase 1 and phase 2, and maybe we can do some sort of a checking, or maybe we can do for some other purpose. So and the driving force is not merely the difference in the concentration of the solute in the two phases. What it says, the driving force for a mass transfer is not the concentration difference in the two phases, but what the driving force is, how far it is far away from the equilibrium, and based on that the mass transfer is going to take place. So when you talk about the how far it is from the equilibrium, there is need to understand what do you mean by the equilibrium. So now what we discuss now, in the maybe for some time we can spend some time on the discussion of the equilibrium. This is what already you learned in the course of on a course in thermodynamic course. There you have learned about importance of the equilibrium, how to do the equilibrium calculations. Now in this case, what we do is we have a closed container. A fixed amount of, let's say, take example of ammonia and air, and is contacted with the water. Then what will happen? there is no concentration of ammonia in the water. So when these two phases are contacted, maybe an interface is going to be formed. So ammonia will be transferring from the ammonia phase to air phase to the water phase, and at the same time the water, there is a little evaporation of the water into the air, or maybe some solubility of the air into water, but when compared with the ammonia transfer, the solubility of the air in the water is very negligible, and the evaporation of water is also negligible. So particularly what is happening, we have a gas phase. The gas phase contains ammonia and air, which is contacted with the water. When it is contacted with the water, now what will happen? The ammonia will be transferring from ammonia air layer into the water layer. So when the ammonia is transferring from ammonia air layer into the water layer, the concentration of ammonia in the water layer is going to be increasing. When the concentration of ammonia in the water layer is going to be increasing, the backward, there is some ammonia which is returning back into the air, which is returned to the air. So ultimately what will happen? So a dynamic equilibrium is established. So when you see macroscopically, there may not be any changes in the concentration of ammonia in the air phase or the concentration of ammonia in the water layer. But the thing is, still the transfer is taking place. Microscopically, still the transfer is taking place. Suppose if you can identify a molecule called as a X in the gas phase, sometimes this molecule will be there in the gas phase, or maybe sometimes the molecule will be in the liquid phase. So what is happening here? Microscopically, still there is a mass transfer is taking place, but macroscopically there is no change in the concentration, there is no change in the quantities. So that situation we call it as a dynamic equilibrium situation. We call it as a dynamic equilibrium. So repeating again, we have a system of air and ammonia, which is the gas phase. It is contacted with the water, which is the liquid phase. There is some solubility of ammonia in the water. So the ammonia will be transferring into the liquid phase. As the concentration of ammonia in the water layer is increasing, some of the ammonia will be returning back to the gas phase. Ultimately, the system is going to reach to a state, we call it as the dynamic equilibrium. Once the system reaches to dynamic equilibrium, macroscopically when you look at the vessel, there is no change in the quantity. But when you talk about the microscopically, when you talk in the microscopic sense, a particular molecule, if you can identify as the X molecule, sometimes this X molecule maybe will be there in the gas phase. Sometimes the molecules of X will be there in the gas phase. So microscopically still the process is going on, but macroscopically there is no change in the process. This is what we call it as a dynamic equilibrium. At a dynamic equilibrium, if you can measure the concentration of ammonia in the gas phase, that you may say Ya. If you can measure the concentration of ammonia in the liquid phase, we can say Xa. So now on a plot that is Xa versus Ya, this can be represented as a 1 point. Now this is the point which is representing the difference in the concentrations of ammonia in the gas phase as well as in the liquid phase. Even though there is a difference in the concentration, Ya is not equal to Xa, but still what is happening, the important, that concept of chemical potential, the chemical potential of ammonia in the two phases are equal, and when the chemical potential of the ammonia in the two phases are equal, then we say a dynamic equilibrium is established. Now what we can do now, we can disturb the equilibrium by injecting some amount of ammonia. We can take ammonia in a syringe and we can inject the ammonia into the system. So now what will happen? That the equilibrium is disturbed, or maybe the equilibrium is disturbed. What is happening now? Again the process is going to take place from the gas phase to the liquid phase, liquid phase to the gas phase. The process will going on, and ultimately it reaches to a new equilibrium. At that time, if we can measure the concentration, this concentration is going to become Ya1, maybe this is going to become Xa1. But this Ya1 and Xa1 little higher than previous Ya and Xa. So we can represent this is the point maybe. Now once the system reaches the equilibrium, again now you disturb the equilibrium by injecting some more amount of ammonia into the system. Then again the process of transfer of ammonia from the gas phase to the liquid phase to the gas phase is going to be taking place. Ultimately the system will come to the dynamic equilibrium. So at that dynamic equilibrium, the concentration now is going to become maybe Ya2, and maybe the concentration is going to become Xa2. So this process is going on, and you can cover almost all the points, and when you are going to join all these points, we are going to get this sort of a relationship, and this relationship we call it as a equilibrium relationship. Equilibrium relation. this relationship we call it as a equilibrium relation, right? So now this equilibrium relationship, when you look at this equilibrium relation, this will give you what is the concentration of a solute in the liquid phase and what is the concentration of solute in the gas phase, and the relationship between these two will give some sort of a curve that we call it as the equilibrium relation. So when you talk about the interface mass transfer, the equilibrium is the most important thing. How far the system is far away from the equilibrium, that is what the most important thing. And now how to calculate this equilibrium concentration? This equilibrium concentrations may be calculated either using a Raoult's law or maybe using Henry's law if the system is gas and liquid systems. If the system is gas and liquid, or the system is gas liquid, or the system is vapor liquid, maybe one can use your Raoult's law, or maybe one can use your Henry's law for the estimations of your equilibrium concentrations. And now what is this Raoult's law and what do you call it, Henry's law? So the Raoult's law applied for ideal solutions, and this says PT, PA, SAT, PA star, that is equal to PA SAT into XA, where PA SAT is nothing but vapor pressure of a component A at a saturated conditions, that is at a given temperature, what is the vapor pressure. Then XA, mole fraction of solute, the mole fraction of the solute substance in the liquid phase, and the PA star is the partial pressure of a component A in the vapor phase. If vapor phase and liquid phase are at equilibrium, concentration partial pressure of a component in the vapor phase if vapor phase and liquid phase are at equilibrium. So this one can use this equation and one can estimate what is the partial pressure of a component in the vapor phase, because vapor phase will not contain only one component, it contains a mixture of the components. So the partial pressure of component A in a mixture of substances is equal to saturation vapor pressure into multiplied by the liquid phase mole fraction if the solution is ideal solution. So now the next question comes into the picture, what do you mean by the ideal solution? And most of the students, they say when you talk to when we ask them what is the ideal solution, they say any solution which obeys the Raoult's law is nothing but ideal solution. That is not right. The reason is, first thing is we are defining ideal solution. If the solution is ideal solution, then one can apply the Raoult's law. The reverse is not right. The reverse is not right. So if that is the case, what do you mean by ideal solution? What do you mean by ideal solution? To tell you the ideal solution, like I can give you one example. If I take 50 ml of ethanol and 50 ml of water, if I mix these two, what is the volume of the solution? Obviously, many of the students, they say it is 100 ml, right? As for your arithmetic calculations, it is right. 50 plus 50 is equal to 100. Maybe some student says it is not 100, it is less than 100. If you ask them what is the reason, they say maybe there is some spillage, maybe there is some volume, some liquid is sticking to the walls of your container. So that is the reason the volume may not be equal to 100 ml, and that is also not correct, because whatever the experiments that we are performing, we have to do the experiments in isolated conditions. So there are no experimental errors, there should not be any spillages, there are no sticking to the walls, and we have to conduct the experiments in such a way that there is no such type of things are going to happen. Then the next question comes into picture. Then what is the volume? The volume may be 100, maybe less than 100, maybe more than 100, right? And you will be wondering why it is. As we know, if the solution is the ideal solution, there will not be any volume change on mixing. That means your total volume minus volume of component A, volume of component B is equal to 0. This is applicable only when the solution is the ideal solution. If the solution is not ideal solution, your Vt minus Va minus Vb may not be equal to 0. So that is the reason when you take 50 ml of ethanol and when you take 50 ml of water, when you mix these two, the volume may not be equal to 100, because there may be molecules are compressing or the molecules may be expanding. So the volume may be little lower or higher than 100, and if that is happening, then we don't call it as an ideal solution. Similarly, if I take 50 ml of ethanol and 50 ml of water, or maybe I can give you another example. I take maybe 10 grams of glucose, which is at 30 degrees centigrade. I take maybe 100 ml of water, which is also at 30 degrees centigrade. Now if I mix glucose and water, what will happen? There is the formation of the solution, and the solution can be, we can use it for the drinking purpose. But the next question is, what is the temperature? Is the temperature is 30 degrees centigrade? Because we are taking a substance A, which is at 30 degrees centigrade. We are taking substance B, which is also 30 degrees centigrade. When I mix these two, obviously one can say, because that is also 30 and this is also 30, so your solution also should be at 30. But this is not again right, because we say the mixing process may be endothermic process, the mixing process may be exothermic process, or there is no, either it is not exothermic process nor endothermic process. So what is happening when you talk about the enthalpy change on mixing, right? That is, the enthalpy change on mixing means delta H total mixer minus enthalpy of component A minus enthalpy of component B. If these are equal to 0, then we can say ideal solution. If this is not equal to 0, then we don't call it as an ideal solution. Now when you talk about the glucose and water, the mixing of glucose in a water is an endothermic process. When mixing of glucose in water is an endothermic process, there may not be any evolution of, the temperature may not be at 30 degrees centigrade, maybe the temperature will be lower than that. So what I want to tell you, if the volume change and mixing is 0 and the enthalpy change and mixing is 0, then we can say the solution is ideal solution. Otherwise, the solution we call it as a non-ideal solution. For what systems there is a possibility of the formation of the ideal solutions, there may be if the solute molecules and the solvent molecules, solute molecules and the solvent molecules have a similar size, solid molecules and the solvent molecules have a similar size and similar intramolecular forces, then one may think that there is a formation of the ideal solution. Otherwise, there is no formation of the non-ideal solution. And maybe we can give you one more example. When you are alone and when you are going to your head of the department or maybe a teacher, what generally you do, we will fold your hands and you ask for whatever the requirement you have. So that means you have some characteristic. And when you go, but now when you are in a group, and again you go to the other department or the teacher and you are asking for something and your behavior is totally changing. You will not folding your hands and you are not the way you ask, that also will not be same as the previous one. And if that is the case, we call it as a non-ideal solution. Otherwise, if when you are alone or when you are in a group, if your behavior is same, then we can say you are an ideal solution. So this is you are going to maintain your identity. Then if you are going to maintain your own identity, then we can get ideal solution. If ideal solution is formed, then one can apply the Raoult's law. Maybe most of the students, this is where they make a mistake. They say what is ideal solution. What is the answer that they are going to give? The solution is ideal solution. The solution is ideal if the solution obeys the Raoult's law. That is not right. Solution is ideal if volume change and mixing is 0, enthalpy change and mixing is 0. That will happen if the solute molecular and solvent molecules have a similar size and a similar intramolecular forces, then there is a chances of the formation of the Raoult's law. So when the Raoult's law is applied, so we have a PA is equal to PA sat into XA, then what we can do, we can apply the law of Dalton, and when you apply the law of Dalton, PA is equal to PT into YA, that is equal to PA sat into XA. So from this what one can say, YA is equal to PA sat divided by PT, maybe we can say some constant or maybe whatever the thing that we have multiplied by XA. So this is for ideal solution. This is the constant Ps add by Pt is constant. So your y is equal to mxa. That means your equilibrium relationship is a straight line relationship, and that constant we can call it as a some constant is nothing but m. Now the next thing is we have a another solution. Maybe another law that is applied is nothing but a Henry's law. So this Henry's law is applied for the dilute solutions. What it says, Pa star is equal to Ha into Pa sat into Pa star is equal to Ha into Xa, where Ha is nothing but a Henry's law constant. So maybe when you talk about the absorption of a gas into the liquid, this is what we have seen in the last class problem when we are discussing about the absorption of CO2 into the water to make a carbonated water. So we know what is the partial pressure of the water, partial pressure of gas in the system. So one can using this relationship, one can find out what will be its concentration in the liquid phase, and this equation is applicable only for the dilute solutions, and this equation cannot be used for the strong solutions. And when you, this also may be written as Ya star is equal to m into Xa, another alternative form of Henry's law, and maybe Pa star is equal to H prime Ca naught. So this is another alternative form of Henry's law. So either it is Raoult's law or the Henry's law. When we look at these laws, one can say the concentration in the vapor phase is different from that of in the liquid phase. That means there is a equilibrium. At the equilibrium, the concentration of substance in the vapor phase is different from the concentration of substance in the liquid phase. So that is what we are going to get some sort of a equilibrium relationship. And now when you have this equilibrium relationship, then what are the parameters which are controlling this equilibrium relationship? Maybe one can use your phase rule. What the phase rule is going to say is phase rule, and this phase rule is nothing but F is equal to C minus P plus 2, where C is the number of components, P is the number of phases, and F is the degrees of freedom. And for this system, what is the system? We have ammonia, air and water system. How many components we have? C is equal to 3. And how many phases we have? There are 2 phases, that is the air phase, gas phase and the liquid phase. So we have 2 phases. Then what is the degrees of freedom? Now your degrees of freedom is going to become 3. What are these 3 degrees of freedom? And that is nothing but your system itself is a 1 degree of freedom. That is nothing but a system of ammonia, air, water system. Then we have a system, we have a temperature is a 1 degrees of freedom and the pressure is a 1 degrees of freedom. That means if you fix the system, if you fix the temperature, if you fix the pressure, your equilibrium relationship is fixed. But if you change any temperature, if you change any pressure, your equilibrium relationship is going to changes, right? Now this is for a system of ammonia and water. Maybe we can have the system of sulfur dioxide and water. Maybe SO2, air, water. Sulfur dioxide, air and water system. Maybe this is the Xa, that is the mole fraction of sulfur dioxide in the water. This is Ya, mole fraction of sulfur dioxide in the gas phase. Maybe we have a relationship like this. Maybe this is 15 degrees centigrade, this is 20 degrees centigrade, maybe this is 25 degrees centigrade, maybe this is 30 degrees centigrade. So as we are going to increase the temperature, for the same value of Xa, there will be more will be the Y value, etc., etc. So what we can say, this now you are fixing the system as SO2, air and water, and if you are going to change the temperature, the equilibrium relationship is going to changes, and that is happening at a system pressure of Pt. Now suppose if you change the pressure also, the equilibrium relationship is going to changes. So what we can say, there will be 3 degrees of freedom for this equilibrium relationship. One is the system itself is a 1 degrees of freedom, temperature is another degrees of freedom, and the third one is the pressure is the degrees of freedom. Now what we can do, we can little summarize what we have discussed. So for the equilibrium relationship, and this equilibrium relationship, maybe one can say the shape of the curve at fixed temperature, at fixed T and P, for a given solute, the shape of the curve at fixed temperature is fixed for a given system. This is the one conclusion we can make. Then the second thing we can say, at equilibrium there is no net diffusion of components. Number 3, we can say, if the system is not at equilibrium, then diffusion will take place to bring the system to steady state conditions. So these are the 3 important points one should remember when you are talking about a equilibrium. And you will be learning a lot of systems, a lot of equilibrium diagrams when you are discussing about your thermodynamics course. There we have a vapor liquid equilibrium, we have a liquid liquid equilibrium, we may have a solid liquid equilibrium. So without this equilibrium data, one cannot solve any problem related to mass transfer operation. So what one can conclude, if you don't understand the thermodynamics, it is not easy to understand the course of mass transfer operation. So one should learn about thermodynamics, or maybe it is a prerequisite course when we are going to discuss about the mass transfer operations. Right? When we are discussing about the applications, we are going to discuss about this sort of equilibrium relationships. But the thing is, this equilibrium relationship is a general equilibrium relationship, may be applied for any gas liquid systems. Then diffusion in phases, diffusion between phases. Right? Now, whenever there is a departure from the equilibrium, then there will be driving force for the diffusion to take place. Whenever there is a departure from the equilibrium, there will be driving force for the diffusion to occurs. Then, and what one can say, the steady state conditions are going to be prevailing. So again, we can to discuss about this diffusion between the phases. Again, we can take the example of ammonia, water, air system, and we can see what will happen, right? And maybe we can say this is the gas phase and this is the liquid phase. So now here we have an interface, right? Maybe I can write a thick solid line for the interface. So at the interface, on one side we have a gas phase, on the other side we have a liquid phase, and in between there is a formation of the interface. Now we can assume that there is a formation of the film on the gas side, there is a formation of the film on the liquid side, right? And you can say there is a concentration profile, that is we have a solute that is nothing but your ammonia, and here we have air. The concentration of ammonia in the bulk of the air, we can say YAG. Now the interface concentration is low compared to the bulk concentration. The ammonia will be transferring through the gas phase, through the film which is formed adjacent to the interface, and reaches to the interface. After reaching to the interface, what will happen? There will be a transfer of a substance from gas phase to the liquid phase. So maybe we can say, and once it is transferred from a gas phase to the liquid phase, then what will happen? The concentration of ammonia at the interface in the liquid phase is very high. So, and whereas the concentration of ammonia in the bulk of the liquid is less, so there will be a diffusion of ammonia from the interface to the bulk of the liquid. So we can say this is the YAI, and this is, we can say, XAI, maybe this we can say XAL, right? And we are going to come across 3 steps. The step 1, transfer of solute from bulk of the gas to interface, right? Then transfer of solute from gas phase to liquid phase. Then the third step, transfer of a substance, transfer of solute from interface to bulk liquid. So there will be 3 steps which are there for the transfer of substance from the bulk of the gas phase to the bulk of the liquid phase. So there will be three steps which are there, and this step 1 and step 3 may be increased or may be decreased by changing the Reynolds number. Suppose we can increase the rate of transfer can be increased by passing the liquid with a very, very high velocity. When you are passing the liquid with high velocity, so your mass transfer coefficient will be very high. So there will be large transfer of ammonia from the interface to the bulk liquid. So similarly, we can increase the velocity of the gas phase. So there will be large concentration of there is a large quantity of ammonia will be transferring from the bulk of the gas to the interface. And the second step, we call it as the interface. This is a geometrical plane. It is a geometrical plane or surface. So geometrical plane or a surface, we call it as the interface, and interface between the two phases. Now, out of these 3 resistances, which resistance is more? Obviously, all 3 resistances are important, which is similar to a student getting a marks in an examination. How many marks the student gets in examination depends on the several factors. How the teacher has taught the course, and how best he has taught, how much we have received, how much you have prepared, how you have written your examination, how the paper was corrected, what was the question paper. So based on that, the students are going to get marks. So there are several resistances which are there. Out of these resistances, what we have to do from our experience, we have to eliminate some of the resistances. Like for example, if the teacher is very, very good, then he teaches well. If the student is also good, then he receives well. If the student put some hard work, then he can prepare well. And now when you go to the examination center or when you go to the examination hall, how you write your examination, what type of question paper that we get it, based on that your marks is going to depend. Maybe other thing is the teacher is not good and we are not received anything. So the more resistance is offered, more resistance is there, how much of knowledge is transferred by the teacher to the student. So what I want to tell you, there will be several of the resistance that we are going to come across when things are moving from one phase to the other phase. So here also there are three resistances are there. One is the resistance through the gas phase, resistance at the interface, resistance through the liquid phase. Now out of these 3 phases, out of these 3 resistance, maybe what Dankwart has said, Dankwart has proved that the equilibrium is going to be established at the interface. The equilibrium is going to be established at the interface in a fraction of second for many of the systems. In a fraction of second, Dankwart proved that equilibrium established at interface in a fraction of second for many of the systems. And for some of the systems, like if I have a air, water and cetyl alcohol, the cetyl alcohol is a surfactant. So when I am going to talk about transfer of cetyl alcohol from the water to air or from air to water, the cetyl alcohol will form maybe it forms some sort of a foaming characteristics, maybe it forms some sort of a big interface when it is forming a big interface, so we are not going to get the equilibrium at the interface. So there the interface resistance is more important compared to the other resistances. So what one can say, out of these three resistances, the resistance 1 and 2 may be important, maybe the resistance 1 is important, maybe the resistance 3 is important, maybe the resistance 2 is important. So, but what Danckwerts has proved, for many of the systems, the equilibrium is established within a fraction of a second. So, the interface resistance is negligible. Obviously, we are going to left over with the 2 resistance. That is the reason we call it as a 2-phase resistance theory. This theory we call it as a 2-phase resistance theory, proposed by Whitman. So, here only we are talking about the 2 resistances, and maybe when you talk about the other applications, maybe we have more than 2 resistance. That is what I told you. For a student getting a marks in an examination, there will be several of the resistance will be there. So similarly, when you breathe oxygen, and this oxygen is going to be stored into a place called as alveoles, and now this oxygen has to reach to the lungs, and when oxygen transferring from alveoles to the lungs, there will be around 7 resistance will be there in series. There are 7 resistance in series. So there may be a more number of resistance, but what your experience is going to tell you which resistance is more. So similarly in this case, what we say, the interface resistance is negligible, only the 2 resistances that are important. Then I can tell you one more example where we have, generally we come across 5 resistance in series, right? What I have a system called a peroperation membrane. This is what I told you. Peroperation is the membrane separation process used for the liquid-liquid separations. Now, I have 2 components, A and B. Both A and B will come to the membrane. As I said already, the A may be having affinity through the membrane. The wave passes through the membrane. So the B is rejected by the membrane. So once B is rejected by the membrane, so we can have a concentration profile like this. Maybe we can have the film like this. Right? Now, the transfer of A from the bulk of the liquid to the interface through the film. Then once it reaches to the interface, it is there in the liquid phase. Now it has to transfer into the solid phase, maybe some area. Once it is transferred into the solid phase, then here the concentration of A is very high. A concentration is a high, so maybe there will be diffusion through the membrane. Once it reaches to the other side of the membrane, it is there in the solid phase, it has to go into the vapor phase. So what we call it as a diffusion through the liquid phase, absorption into the membrane, diffusion through the membrane, desorption into the membrane, desorption from the membrane. Then once it is desorption, then it has to go into the bulk of the vapor. So this is the one resistance. There are 5 resistances in series. So experience is going to tell you which resistance you have to take into the consideration. So in this case, what I said, the first maybe resistance 1 and resistance 3 are more important compared to the resistance 2. That is where we call it as a 2-phase resistance theory, which is proposed by the Whitman. And now we are going to come across another problem. The problem is, at the interface, this temperature, the bulk of the gas is at bulk of the gas is at temperature T, bulk of the liquid is also at temperature T. So the interface is also at a temperature T. So because we know the temperature, we know what equilibrium relationship that you have to use. Now, in some systems, as we discussed, the solute is transferring from the gas phase into the liquid phase. When the solute is transferring from one phase to the other phase, there may be evolution of heat, or maybe there is a absorption of heat. And because of this, the temperature at the interface will be different from the temperature in the gas phase and the temperature in the liquid phase. Now, a question arises, which temperature you have to use it. And if once the temperature is changed, then obviously your equilibrium relationship is going to change, and we may say that this equilibrium, your concentration is the system is far away from the equilibrium. That is not the right. The system is far away from the equilibrium when all the things are at same temperature. So the problem of the complexity is going to be increasing, and once the problem of complexity is increasing, the numerical solution is also going to be taking more time, and this is where you understand, as we are going and going, the complexity in chemical engineering is going to be increasing. Now, one may observe here at the interface, the concentration of the solute in the gas phase is lower than the concentration of the solute in the liquid phase, and it is not a barrier for the diffusion, because even there is a low concentration here, there is a high concentration here, but the chemical potential of the component the chemical potential of the component in the gas phase and the chemical potential of the component in the liquid phase, both are equal. So that is where we can say equilibrium is established. So whether this point is above or this point is below, one need not worry about this. So even this concentration higher than this concentration, the chemical potential and the transfer is taking place at the interface, because the chemical potentials are equal. So one should not be worried about this point here. Then we can say, now we can represent these concentrations on another graph sheet, or this concentration can be represented on equilibrium relationship. Equilibrium relationship is XA and YA. We have equilibrium relationship like this, and we have YAG, and maybe here we have a XAL. So this is your point. Now this is your initial concentration of solute in the gas phase, initial concentration of solute in the liquid phase. Now we have to estimate the interfacial concentration, and for the estimation of interfacial concentration, that is nothing but you can say P, right? Maybe at the interface we have concentration is YI and we have concentration is. So now this line, when you join this line, that will give your interfacial concentration. As we discussed already, steady state conditions are prevailing. Steady state conditions are prevailing means how much of the solute is transferring from the bulk of the gas to the interface, same amount of the solute is transferring from the interface to the bulk of the liquid. So that means when you assume that the steady state conditions are going to prevail, there is no accumulation of the solute at the interface. If that is the case, what one can write for the gas phase, your flux of a solute A is equal to mass transfer coefficient Kg multiplied by maybe Ky multiplied by YAG minus YAI, where YAG is the concentration in the bulk phase and YAI is the interfacial concentration. So YAG minus YAI multiplied by the mass transfer coefficient for the gas phase, that is equal to flux. This also should be equal to Kx into XAI minus XAL, right? Or we can say YAG minus YAI divided by XAL minus XAI is equal to Ky by Kx. So this is the most important relationship, and this equation can be solved if, because here YAG, the concentration in the bulk of the gas is known to us, the concentration in the bulk of the liquid is known to us, and the concentration, interfacial concentration YAI is known to us, the interfacial concentration, YAI is not known to us, the interfacial concentration XAI is not known, and Ky, the mass transfer coefficient in the gas phase, the mass transfer coefficient in the liquid phase. So whatever the way we have calculated the mass transfer coefficients in the previous module, one can estimate the mass transfer coefficient for the gas phase by knowing about its Reynolds number, and one can estimate the mass transfer coefficient for the liquid phase by knowing about its Reynolds number. So because we have a correlation for the estimation of mass transfer coefficient for the gas phase, we have the correlation for the estimation of mass transfer coefficient for the liquid phase, and this can be done if you know the Reynolds number. So estimation of Ky and Kx is not a problem now. And now in this equation, if you are going to see, there are two variables are there now, two unknowns that are there, YAI and XAI, but we know there is a functional relationship, YAI is equal to function of XAI. So maybe the simple Henry's law, if you are going to use, YAI is equal to M into XAI. So now you know YA is equal to M into XAI. Maybe we can substitute these values here, and one can solve for what is the XAI, then one can solve for the YAI, and this is given by minus K, and that is when you are representing on a graph sheet, this is the equilibrium relationship, and this is the XAL, this is the YAG, and after representing YAG and XAL, we can substitute the point here, and we can draw a line with a slope of minus Kx by Ky. Where it touches the equilibrium diagram, that will provide the XAI and YAI. So if we have to estimate the XA, if we have to estimate the XA and YAI, we have to estimate the KX, KY, and it is not so easy to as we have already seen. For each situation, estimation of Kx and Ky itself is a very complex thing, and estimation of YAI and XAI is a complicated thing. So what we have to do now, we have to do something else other than that for the estimations of the fluxes. Maybe in the next module we are going to discuss about how are you going to estimate the flux when the two phases are brought into contact. Thank you very much.